So thank you all for joining me this morning to hear about the research I've been doing these past couple of years. I really appreciate you all showing up, especially those of y'all who are different time zones where it's not, I guess, in the morning. But so hopefully you all know me. My name is Hagen, talking about all the research that I've done these past couple of years. And one of the things that I've done really well, I think, as a graduate student is really how to create a succinct title that really captures the essence of the research that I was doing. So I'm going to read this real quickly for you. But talking about the development and application of consumer-grade sensors to gather ecologically valid and multimodal environmental data to characterize indoor air quality and determine its effect on sleep quality. So I know it's quite a mouthful, so I'm going to kind of dive into each component of the title here and talk a little bit about, kind of define the terms within the title. So when I say consumer-grade devices or consumer-grade sensors, these are devices and sensors that use the same fundamental processes as research grade monitors, but at a fraction of the cost. So rather than spending thousands of dollars for one sensor, you can get 100 of these consumer grade sensors for the same price. So this allows us to monitor more spaces in parallel, so we can monitor more participants, get more data, which allows us to make a little bit stronger, statistically significant conclusions. And it also gives us greater availability. So we're not having to fight for the use of one or two really good research grade monitors. We can just kind of get our own devices and tailor them to our own research project. And then lastly, there's less worry associated with them. So because these sensors are a little bit more affordable, we can send them out into the field and we don't necessarily care too much if they get damaged, lost, or stolen versus a thing, a device that costs $1,000 or tens of thousands of dollars. That's a little bit more of an issue if that gets damaged or lost. So then we can use these consumer grade sensors to gather ecologically valid and multimodal environmental data. So in terms of ecologically valid, we essentially want to run an experiment where the participant doesn't even realize that they're in an experiment, right? So this allows us to generalize those results to a larger portion of the population, rather than bringing participants into a sleep clinic or having these loud sensors that kind of have a tick every time they measure. Ideally, they wouldn't even realize that those sensors are there. So this introduces less bias into our results, and that's why the ecologically valid component is a big key component. In terms of multimodal, we're using indoor air quality sensors to get that environmental data. We're using wearable fitness trackers to get things like sleep quality data and activity data, phone sensors, so things like GPS and accelerometer data, and then surveys that give kind of snapshots of the environment with which our participants are living in. Also allows us to get sleep surveys and mood surveys. So not necessarily all environmental data, but definitely multimodal. And so we can gather this ecologically valid data with consumer grade sensors to characterize the indoor air quality data. And then the big question I wanted to look at was, what is indoor air quality's effect on sleep quality? So characterizing indoor air quality, that's simply just monitoring the concentrations, looking at the concentrations, doing some analysis, what are the sources of those, doing things like calculating ventilation rates. And then once we have confident and we have trust in those results, in those measurements, we can then relay them to human health effects, in this case, sleep quality. So for sleep quality, there should be an association, right? Both indoor air quality and sleep quality are very much related to breathing. And so there should be that association, but there's limited research. And that kind of goes back to the fact that we haven't really been using consumer grade sensors to explore this relationship. And it's very cumbersome to kind of do this analysis with a research grade instrument. And then we have to kind of look at this difference between self-report sleep versus measured sleep. So all in all, using consumer grade sensors to gather ecologically valid data to explore relationships between indoor air quality and human health, essentially, is what I've been working on these past couple of years. So I find all this stuff very interesting, and you should too, because it's very relevant to your life. So each of these numbers here on my left, I'm not sure if you have your screen here or not, but it's on my left. They exemplify a number of years. So that 79, that's the average US life expectancy as of 2020. And about 89% of your life, so 69 years, you will spend indoors. So this isn't necessarily your home, but between kind of work and home and different spaces, you'll spend a surprising number of years indoors. So what that means is that the exposures to indoor air pollutants that you kind of accumulate over your lifetime are very important. So it's not just the acute exposures that kind of make the headlines that are important, but also just slightly elevated concentrations that you're going to be exposed to over a period of 69 years. So this kind of shows how important indoor air quality is in monitoring indoor air quality and making sure those concentrations are safe. And then 23, that is the number of years you will spend asleep. So it's about an average of 7.1 hours per night that you're sleeping. And for this one, where you could argue the time spent indoors is probably split between places like work and home, I would argue that the majority of those 23 years, maybe 20 of those 23 years, are spent in your own bedroom, right? You typically sleep in your own bedroom. So that means the sleep microenvironment is also very, very important. Coupled with the fact that you're in a semi-unconscious state while you're asleep and you don't necessarily have full control over your environment. So it's only going to be kind of these dramatic changes in indoor air quality or temperature or relative humidity that are going to wake you up and allow you to kind of change that environment. So that's kind of why I like the research that I do, is because it's very important to many of us, right? Because we're going to be spending time indoors, and I can guarantee that you're going to be spending time asleep, right? So that's why I enjoy the work that I do, because it's relevant for so many people. So how do consumer grade sensors fit into all of this? There's been kind of this explosion in consumer grade sensors in the indoor air quality field and the outdoor air quality field over about the past 15 years or so. And we're starting to trust these results from these sensors more and more, as researchers have shown that they can be successfully calibrated against references. They can be deployed in all various kinds of configurations, and they produce data that's very, very similar to the reference grade monitor. The biggest issue, of course, with consumer grade sensors, because the circuitry is simplified, because the hardware is a little bit simplified, you're making things kind of in batches. They tend to be less accurate, of course, than reference grade. But if you calibrate these devices, they can provide some valuable measurements. But now that we've proven that consumer grade sensors can give us these trustworthy results, we need to move beyond just monitoring indoor air quality, just creating these networks and saying, hey, it works, right? We need to start linking the indoor air quality data with other streams of data. And so that's kind of my motivating question behind all the research that I do, is how can we use consumer grade sensors in a research context to explore some more complex problems. And so this question I've kind of broken down into kind of 4 sub-questions. They almost function more as steps, I guess, along my path. So this first question is addressing the knowledge gap that exists between these two groups. So you have the indoor air quality scientists who know a lot about air quality. If I say, hey, here's the pollutant, here's the measurement, they can say that's good, that's bad. They understand ventilation, they understand what should be the concentrations within those spaces. And then you have people, embedded systems engineers, right? Like electrical engineers, computer scientists, who can make these really, really nice devices that are very, very reliable, build out their own device and deploy them. But a lot of times when I read studies from that second group, they report results and the numbers just don't make any sense. The concentrations that they're measuring just are outlandish, right? And so we need kind of this combination between the air quality scientists who know, what values make sense, with the embedded systems engineers who can make these really nice devices. Once we make these devices, we need to calibrate them, right? We need to develop these methods so that we can calibrate them effectively, so that we can start to trust those results. And we need to do it, if you're in that second group, you might not have access to reference grade monitors or controlled spaces or compressed gas cylinders where you can kind of inject known concentrations into a space. So kind of the idea behind when we were calibrating was, okay, what kind of spaces can we use? What kind of processes can we use, so that you can kind of get an idea that if you don't have these resources available to you, how good of a calibration can you get? How much can you trust those results? The third question is, okay, if we just have indoor air quality data, what kind of neat applications beyond just monitoring the air quality can we do with this data? And then lastly, now that we can trust these results, now that we've shown that we can send out these devices and get back data, what other data sources can we link air quality with to start exploring more complex relationships that are very cumbersome and challenging to do with traditional monitors? So each of these questions I've kind of compiled into 3 different chapters that kind of will be the outline of this presentation going forward. So the first part there is about developing an affordable indoor air quality monitor. This helps us address that knowledge gap, because I, with an environmental engineering background, am trying to create my own device. And then we also did a very targeted calibration. That second chapter there is about some of the applications of consumer grade sensors, occupancy detection and ventilation estimation. And then the last one is the big question that I wanted to set out to look at, and that's understanding the relationship between indoor air quality and sleep quality. So this first chapter, right, developing an affordable indoor air quality monitor, we built what we call the Building Environment and Occupancy Beacon, or the BEVO beacon, named for obvious reasons. You can see the different parameters that we're measuring there. The nitrogen dioxide, carbon monoxide, and carbon dioxide sensors also have temperature and relative humidity modules built into them, so we're getting that data. We have that little blue sensor on top that's a light sensor. And I guess I can explode this out and show you all the components. On my left, the blue kind of credit card looking device, that's our printed circuit board. Allows us to make all the connections between our sensors and the brains of the device. In the middle, we have the plywood that we laser cut in the Invention Works on campus. A little bit of a tension between myself and some of the coworkers in there because you can see we laser cut about 50 of these devices. So I was in that space quite a bit. Didn't necessarily like me using the laser cutter so much, but I had to make these devices. And then on the right, you can see all the different components. In the middle there, kind of under all the wires, is that PCB. Some of the components I didn't mention earlier, we had a display on the device, RTC, that's a real-time clock, so it keeps time for us when we lose Wi-Fi, it's battery powered. We have a fan to kind of help with heat management. And then you can see the CO sensor and the NO2 sensor, those are connected via USB to a Raspberry Pi, which is the brains of the whole device. So that's a bare bones computer that allows us to run some Python scripts so we can pull data from those sensors, store it locally, and or push it up to the cloud. So now packing all of these devices together, we can co-locate them with reference grade monitors and do some calibration. So the typical kind of flow is shown there on the left, and the figures I'm showing you on the right are for the calibration we did for carbon dioxide and particulate matter, both in the U-Test house, which is kind of a full-blown home environment. Well, it is a home, but it's on Pickles Research Campus. And then the environmental chamber, which is an 8 cubic meter controlled chamber. So generally, I would run 3 experiments where I would generate some typical concentrations. So in this case, carbon dioxide and particulate matter concentrations. Create univariate linear least squares models. So your good old-fashioned y equals mx plus b by comparing the reference to the BEVO beacons measurements. And then for each experiment, I would average the m's and the b's from those equations and create a final averaged model that I would apply per sensor, per device, and then run a 4th experiment to see how well those models perform. So for TVOCs, we didn't have a reference monitor, so we had to kind of use the average. We used a reference that was the average of all the sensors measurements. For temperature, we did kind of a similar experiment. We did in a smaller incubator that we could kind of mess with the temperature, and I only did 1 experiment per those devices. And then for CO, we did a more, I guess, a fancier calibration where we had the devices in a small chamber, a very well sealed chamber, and we would inject carbon monoxide at various concentrations into a step calibration. So like I said, trying to do different environments, different processes to try and get at how good of a calibration can you get. And then once we were done calibrating, it was time to roll the sensors out into the real world. So we had a beta test that was about 20 or so participants over 3 weeks in, I believe it was February of 2020. And then that allows us to debug the devices a little bit, figure out what we need to kind of change for the big study, the cohort study we call the UTX-1000 study that we conducted the summer of 2020. That was with 30 participants, and it was over 11 weeks during the summer. And you can see those measurements there. So what I'm showing you is the distribution of measurements for each of the participants within that study for each indoor air quality parameter. And so for the most part, all these measurements are within typical bounds, especially when you look at kind of more vetted sensors like CO2 and particulate matter. The carbon monoxide are a little bit higher than perhaps we would expect, but that sensor technology is a little bit more limited. And then the temperature, those are a little bit high, and that's just because the BEVO beacon was a little bit hot. You have all those components stored in the device. It tends to be a little bit hot. So those are about maybe a degree and a half warmer. But still, you can look at these results and see that we're getting reasonable measurements from these sensors that are much more affordable than kind of 1 reference grade. And we can do these really lengthy studies, right, 2.5 months, and we can have 30 participants versus if we used a reference grade, we could only do maybe 1 week or maybe a couple days in 1 participant, and then we'd have to keep moving the devices around. It gets very challenging, whereas we can just do this in 1 fell swoop. So now that we have these measurements, we can start to do a little bit more unique analysis, like I said, by doing things like occupancy detection and ventilation, estimating ventilation rates, rather than just showing the results like I did. So most studies tend to kind of stop at that last figure there and say, hey, we built this device, we deployed it, and that's it. So we wanted to go a step further and start to characterize the indoor environment beyond just monitoring that indoor air quality. So I want to take a small step back and kind of talk a little bit more about that UTX-1000 study, because it's very important. All the data that will be in this analysis, as well as the sleep quality and indoor air quality, is coming from the UTX-1000 study. So the BEVO beacon, as I mentioned before, that's where we're getting our indoor air quality data. That is measuring the bedroom indoor air quality. So it's important to note that we put that in. Well, we had participants place it in their own bedrooms. We have the BEVO app, which gives us GPS data from the phone. And it allows us a way to disseminate sleep surveys. So we get 4 subjective measures of sleep. And then lastly, we have our Fitbit. So this detects those sleep events, and it allows us to get 3 more sleep metrics, this time a more objective measure of sleep. And like I mentioned, this was during the summer of 2020, about 11 weeks. If you'll notice, that number from 30 changed to 20, and that's because I have to have overlap between all 3 of these data sources. When I don't have overlap, I can't use that participant. So unfortunately, we lost 10 participants, whether or not the BEVO beacon was left unplugged, or they didn't allow location services on the BEVO app, or they just decided not to wear their Fitbit for whatever reason. So we kind of lose a few participants there. But this again shows kind of the power of consumer grade sensors, right? Because all of these are very affordable, right? The app costs us nothing. The Fitbit is as cheaper than the BEVO beacon, right? So we can disseminate all these different modalities. And it's okay if we lose data, because we still have 20 participants. We still have weeks of data to look at. So for all these analyses, we had to kind of determine occupancy, because we conducted this study in the wild. We don't necessarily know if the participant is in their bedroom or not. So we needed to do some occupancy detection on the surface initially. And so the first method we did was kind of this data fusion approach. And so that simply is saying we're taking information from each of those 3 modalities, combining it to get confident estimates of when that participant is in their bedroom. So working through kind of an illustrative example here, if we have continuous indoor air quality data and more or less continuous GPS data. You might have noticed we conducted this study during the summer of 2020 when things were getting a little bit hairy, and so we had to actually distribute all of our devices out to participants across Texas. And so that allowed us to get their addresses, which we could compare to the GPS data and determine when they're home. But now this is not quite good enough, because we need to know when they're in their bedroom, right? Because the BEVO beacon is in their bedroom. So what we can do is we can overlay the sleep episodes, and that's a pretty good assumption that when you're asleep, you're going to be in your bedroom. Now, I know you can fall asleep on your couch or whatnot. So we looked at the indoor air quality data to confirm that those participants were in their space. The bedrooms tend to be a little bit smaller, and we are a source of CO2, right, when we exhale. And so that CO2 concentration in general should be increasing throughout the night up to a certain concentration. Now, there are times when the CO2 has a little bit more fun of a journey, and that's typically because the ventilation is kicking on. So we would look at the CO2 as well as the temperature, and if they kind of have a similar trend, that's a good indication that the ventilation system is strong enough to remove some of that CO2 and provide cooling. This is the summer in Texas, so it's always a cooling season, so the AC will always be turning on to cool rather than to heat. So that was how we kind of determined occupancy within the bedroom, which was important for the ventilation analysis, as well as, of course, indoor air quality and sleep quality. But we also had all this other data when we knew participants were not home. And so that allows us to label the indoor air quality data from periods when people are home and when they are not home. And so what we can do is we can train a machine learning model off of these labeled indoor air quality data, so that we can learn periods outside of the sleep episode when that participant was home, right? Maybe they're taking a nap during the middle of the day that Fitbit doesn't recognize, or maybe they're studying. So we can train the machine learning model to say, hey, this indoor air quality data looks a lot like the data when they were sleeping. So I'm going to predict that they're probably in their bedroom. So we can split the occupied and unoccupied tagged indoor air quality data into a training and test set, and train a few machine learning models to see if we can predict that occupancy with a reasonable accuracy. And we can. So we trained 4 different machine learning models: logistic regression, naive Bayes, random forest, and a multi-layer perceptron, which is just a simplified neural network. And what I'm showing you is the accuracy of that model to predict occupancy based on just CO2 and TVOC concentrations for each participant, labeled there on the bottom on the x-axis. And that 80%, that's the average accuracy of the MLP model for each participant. And in the realm of machine learning, 80% is a pretty good accuracy score, right? So what this shows is that even with consumer grade sensors who don't necessarily have the most accurate results, we can still get a very, very accurate model to predict occupancy within a space. And the MLP, the neural network, isn't that fancy of a model, right? So we can do this with even just simplified models. If we had kind of maybe used more robust machine learning methods, we could even get that accuracy a little bit higher. So now that we have periods when we are confident that the participant is in their bedroom, we can start to do things like estimating bedroom ventilation rates. And so you can do a single zone mass balance on carbon dioxide to get at what that ventilation rate might be. And so this equation here, I won't necessarily go into all the details of each term, but to look smart, I got to put an equation on the slide, right? So that first term on the left of the equal sign, that kind of tells you the change in concentration with time in a space. The term just to the right, that's the flow of carbon dioxide into the space from outside of the room. The QC, that's the flow out of the space. And then E, that's the source, that's the emission term in the room. So in that case, that would be you or the occupant. And we can get at what that emission term might be looking at the temperature and pressure in space, which we're getting from the BEVO beacon, the body mass ratio, which we get from the Fitbit, and the metabolic equivalent, which we can get from Fitbit, but we can also make an assumption that it's relatively low. So metabolic equivalent is a measure of activity level. So most of these periods are from when the participants are asleep. So we can assume kind of a low metabolic equivalent or low activity rate. And then depending on the conditions of the CO2 in the space, we can calculate that ventilation rate. We can simplify that mass balance equation. So in the first case, that's the steady state assumption. So, well, not assumption, that's the steady state estimate. So this is when that carbon dioxide, about after an hour or so, reaches a plateau and starts to taper off. So in that case, the change of concentration with time is zero, right? The concentration is staying relatively stable. So that whole term on the left side of the equation goes away. And we can rearrange the equation and solve for lambda. So that is the air exchange rate. That is the flow Q divided by the volume V. That's a measure of ventilation in the space. We can also do a more dynamic approach where we look at the initial increase in concentration once the participant enters the space. So now we're solving for the concentration with respect to time at each of these points. And what we're trying to do is we're trying to calculate the concentration at each of these times by varying the lambda, which you can see is now in the exponent, to match our calculations with what we measured. So if we can reduce that error between the calculated and measured, that's kind of what that air exchange rate would be. And similarly, we can do it when the participant leaves the space. So now rather than capturing the beginning or the middle, we're capturing the end. And you'll notice that the participant is no longer in the space. So that E term, that emission term is gone, the capital E is gone. And then we're doing the same thing where we're trying to toggle that lambda so that we match what we calculate with what we measured. And so these are the ventilation rates that we were able to estimate in white. That's the steady state concentration or the steady state estimate. In burnt orange, that's the buildup. And in blue navy, that is the decay estimate. And so I'm showing you the ventilation rates in inverse hours. And so what that essentially means is that for a ventilation rate of 1 inverse hour, that would mean the whole volume of your space is completely replaced by a whole new volume of air. And if you look at participants such as like participant 10, 21, 26, 38, they all have consistent estimates across the various methods, which is somewhat surprising in the sense that we're using all these different estimation methods. We're making various assumptions within each estimation method. And again, we're using data that people don't tend to trust because it's coming from the consumer grade sensor. Yet we're still getting very, very good numbers here. And what's also important to point out is that I didn't have to do like any outlier removal on these data, right? The max air exchange rate we got with is 2.5. There's no like 10 or 15 that just kind of came out of the data. All the data is shown here, which again, it's not the norm, especially when you're dealing with consumer grade sensors. So within participants, we're getting pretty consistent measurements and also across studies, right? So if you look at on the right there, the related studies were well within those ranges of estimates. And those related studies are review studies. So they're studies of studies. So there's many, many studies that are baked into those ranges. And those studies are using fancy reference grade multi-$1,000 monitors to monitor CO2. And they're also using consumer grade sensors like we're using to get those ventilation rates. So very promising that our data is still falling within those ranges, even when we have some assumptions that kind of skewed our numbers a little bit. And we're using consumer grade data or consumer grade sensor data. So in these last couple of minutes here, I want to talk about the big research question that I wanted to explore, and that's the relationship between indoor air quality and sleep quality. So to kind of start this discussion, I wanted to look at the associations between indoor air quality and sleep quality. Because as I mentioned before, there should be a relationship between indoor air quality and sleep quality. So the first one is that you have pollutants like PVOCs, particulate matter, NO2, and others. That when you inhale slightly elevated concentrations of these pollutants, your airways are going to become inflamed. It's going to obstruct your airway. It's going to make it harder to breathe. So if you have a pre-existing condition like sleep apnea, or you tend to snore a lot, this is going to make your snoring or your issue even worse, right? So it's going to cause you to sleep a little bit worse, right? You're going to have a little bit more broken sleep during the evening. Some pollutants like carbon dioxide, they just cause excessive drowsiness. And these are at concentrations that aren't unheard of in the indoor environment. So, when you start thinking about a conference room with a lot of employees in there, or a classroom with a lot of students, those concentrations can routinely hit, 2,000, 3,000 parts per million, which at those levels, you start to see this drowsiness appear. The air just starts to feel a little bit stuffy and you just kind of want to take a nap. So next time you fall asleep in your meeting, you can blame the CO2 concentrations. But that's just this idea of excessive sleepiness, that CO2 is just causing drowsiness. And then you get to pollutants like NO2 and particulate matter, and especially ultrafine particulate matter that can penetrate the blood-brain barrier and start to mess with the neurotransmitters in your brain. And so that starts to disrupt your normal circadian rhythm, which starts to influence how you sleep and the different stages that you hit during the evening. So a good example of this are people who smoke a lot of cigarettes. They tend to have a lighter level of sleep and they don't hit those deeper stages as often, or if they do, they kind of hit them and come right back out relatively quickly. And so that's because when you're smoking cigarettes, NO2, PM, CO, those things are going to be in small concentrations within that cigarette smoke and what you're inhaling. And so that's going to cause some disruptions with your sleep. So going back to processing this data to do this analysis, if I show you that little snippet of the visual I mentioned earlier, we're not looking at the data that we found via the occupancy detection models. We're just looking at the data from periods when we knew the bedrooms were occupied based on Fitbit data, the sleep episode, and that we had GPS data to confirm that participants were home. And so what we would do for each indoor air quality parameter for each night, we would take the median of that parameter and compare it to thresholds that are more or less established in the indoor environment. Most of the standards are for the ambient, the outdoor environment, versus compared to the indoor environment. But we can still compare them. So, for instance, if we take CO2, we would take the median CO2 concentration during the evening. If it was, let's say, 1,000 parts per million, and we look at the threshold, it's 1,100. We'd say, okay, that for that night, the CO2 is at a satisfactory level. So that's a good air quality night. If it was 1,500 parts per million, then we would say, okay, that night was bad. It was an unsatisfactory night. And for most of these, they're based off of some sort of standard established by some sort of body like the WHO or ASHRAE. But for temperature, again, as I mentioned before, our temperatures tend to read a little high. So to kind of offset that and to get around the kind of weirdness that's associated with the ASHRAE thermal comfort standard, we just kind of used the median concentration from our analysis, which kind of helped correct a little bit for that higher temperature that we experienced during the night. And so for each night, I would do that analysis for each parameter across all the participants, and I would determine the distribution of sleep metrics for nights when the indoor air quality was bad, and compare it to the distribution of sleep metrics for nights when that indoor air quality parameter was good. And then I would look if there was any statistical significance between the two means of those distributions, and to see in what direction that significance was in. And so that's what that table on the right is showing you. So again, if we stick with CO2, the point is to kind of read the table from left to right. So if you look at CO2, what I'm saying is that for nights with elevated CO2 concentration, we saw a decrease in self-reported restfulness. So participants were feeling less restful when they woke up in the morning. And we're seeing that participants tended to fall asleep a little bit faster. So SOL is sleep onset latencies. That's the tech term or the scientific term for how fast you fall asleep. So sleep onset latency. So we saw that had decreased when CO2 was elevated. So that kind of goes back to the fact that I mentioned when CO2 is high, you tend to get a little bit more drowsy. So perhaps that CO2 is helping you fall asleep. However, when we look at Fitbit, we look at the objective measure, we see a decrease in total sleep time. So that's the amount of time that you're actually asleep when you're in bed. And so now we're saying that CO2 is elevated, but people were sleeping less, which kind of goes against that initial connection that I had made. So you can kind of read the rest of the associations there. But in general, what I'm saying is that for elevated TVOCs and particulate matter, we see an improvement in sleep quality, which kind of goes against our hypothesis. And the reason for that is that we weren't seeing, especially for particulate matter, we weren't seeing concentrations that are outside the norm. We were seeing concentrations between 10, 20 micrograms per cubic meter, which for a place like Austin is pretty common, perhaps a little high. But again, you have to kind of take these with a grain of salt because we're using consumer grade sensors. If these concentrations were 40 micrograms per cubic meter or 50, I think we would start to see a flip in that relationship. I'm very confident that that would be the case, but we just didn't have those high enough concentrations because, Austin, well, I guess this is all across Texas. So Texas tends to be a pretty clean place. However, for places for compounds like CO and CO2 and for temperature, we saw a decrease in overall sleep quality across self-report as well as objective measured by the Fitbit. However, the sleep onset latency did decrease when CO2 or temperature was high. And so usually to a certain extent, you want to fall asleep faster. If you're falling asleep within 5 minutes, that's more of an issue. But if you're falling asleep between 5 and 10, that's typically good. So when that SOL decreases, that is a good thing. And the reason for that is if you look at the other sleep metrics here, sleep onset latency is the only metric that's associated with the beginning of your sleep, whereas the rest of these metrics are associated with the entire sleep episode. And so it very well could be that your sleep onset latency, your air quality at the beginning of your sleep episode was very, very good. And so that's why, SOL is only affected by that air quality at the very beginning of your sleep episode. But we're taking the median from the entire sleep episode where, for the most part, these indoor air quality parameters tend to get a little bit higher. So the median is probably from somewhere later in the evening versus in the beginning. And then lastly, elevated TVOCs and particulate matter, they were associated with changes in sleep staging. So that's that REM, rapid eye movement to non-rapid eye movement ratio. And you can see that if you look on the right there, those relationships are in different directions. So not necessarily a good or a bad thing, but there was a statistical significantly different mean between those two distributions when TVOCs and PM2.5 were elevated versus low. So that kind of goes back to what I said about TVOCs and PM2.5 being associated with cigarette smokers and kind of changing the sleep staging. So it is proving that association, at least to a certain extent. So kind of some sort of general conclusions here. We're seeing a shift away from just solely reference grade monitors in both the indoor and ambient air quality monitoring fields. We're not replacing reference grade monitors in total, and I don't believe we should. I think we should use a combination of the two, because consumer grade sensors allow for a kind of a wide variety of advantages over your traditional monitoring, which I've kind of mentioned before, but I'll reiterate here. So these sensors are more affordable, so that allows us to purchase a lot more of these sensors, which allows us to monitor a lot more environments. And especially in the indoor air quality field, this is very, very important because the concentrations of things like CO2 can vary from room to room, but even also building to building, right? Whereas you can, for the most part, get away with a really good reference monitor for a block of a city for the ambient air quality. So we need more scalability and to kind of target these different environments for indoor air quality applications. And that goes back to that scalability. Because they're so affordable, we can kind of send them out to various places and get that data. In terms of availability, we don't have to vie for these sensors being available, right? If there's 10 graduate students trying to use one really, really good reference monitor, we don't have to fight over when we can use it and schedule it around it. We can just tailor our own sensors, buy our own sensors, and tailor them to our own environment. That's one way of reducing hassle. What I mean by hassle is we don't have to worry about if these sensors get lost, damaged, or stolen, all three of which happened to the BEVO beacon at some point. It's not the end of the world, right? We can easily replace some of these sensors. It's more affordable. We have that in the budget. We can take care of that. And it allows us to target some of these applications that, again, would be tricky with traditional monitors, right? There's no way I would be allowed to take, the 10,000 or I don't know how expensive it is, sensor we have for particulate matter and put it in some random person's bedroom in Houston. Like, there's no way that would be a thing I could do. So we have to kind of use these consumer grade sensors because we don't want those sensors getting damaged and because we don't know what's going to happen with them once we release them into the wild. And that's that big thing the big point at the bottom there is, right, is we can do these measurements in an ecologically valid manner. and we're introducing less bias, and so we can take the results we get and say, hey, these can be generalized at least to a subset of a larger population, which is really, really important. In terms of the specific research questions, I didn't mention it, but the BEVO beacon is entirely open source, and it's documented by someone who has no idea what they were doing with electrical engineering and embedded systems engineering, right? So it should be a repository and a source for people for indoor air quality scientists who want to make their own device, to be able to go in and see all the documentation and build their own device. I'm not saying they had to build a BEVO beacon, but at least they have a good starting place to kind of make their own device. And we used a variety of components on the device, and so that allows, if the researcher wants to use sensors that are like our CO2 and particulate matter sensor, they can read up the documentation on just those. Those sensors were very different from the NO2 and the CO sensors that we used. So if there's another researcher who's using sensors like those, then they have an opportunity to learn about that documentation, right? So it kind of opens up the field a little bit so they can kind of explore their own design. In terms of calibration, the idea was to kind of tackle all these different kind of calibration scenarios to kind of give a sense of what calibrations are successful, what ones aren't, what kind of quality are you going to get out of these calibrations, especially when some resources aren't available. We used univariate least squares models. I think least squares models work very well. Univariate might not be the approach for compounds like particulate matter. You might want to include temperature and relative humidity into that model, probably make it a little bit more robust. But what we did find was that device-specific models are the way to go. And what I mean by that is you need to make a model per sensor per device. You can't just make a model for the CO2 sensor and apply it across all 50 BEVO beacons. Because if you go out and buy even a $200 sensor and you buy two of them, you place them right next to each other on your desk, they're going to read entirely different values. So you have to calibrate these devices, and you have to calibrate them specific to the individual device. In terms of that third question, hopefully I showed you that the application of these consumer grade sensors, we can trust some of the measurements that are coming out of them a little bit more than perhaps originally thought. With just using CO2 and TVOC measurements, we detected occupancy on an average of 80% with that neural network model. The CO2 tracer method, it gave us reasonable estimates of ventilation. They were well within typical bounds we'd find in the indoor environment. Some of them, of course, were a little bit high, but I would actually attribute that not to the data coming from the sensors, but from the assumptions, like the assumption we had to make on the volume of the space, which really drove those values to be a little bit higher or lower than maybe perhaps what they were. So I think the data itself was good, but some of the assumptions on the back end were kind of the issue. And in terms of indoor air quality and human health, in this case, sleep quality, we saw that the effect depends on the AIQ parameter, which of course makes sense, and the concentration. Like I said, I think those relationships between TVOCs and PM2.5 and sleep would be different if those concentrations had been, outside of healthy, normal bounds. And it depends on the sleep measurement technique. So both have value, right? A self-report perceived sleep quality has just as much value as what how well you slept on paper. So you have to include both of these in your analyses because they're very important in terms of determining what that relationship is. So lastly here, kind of the future of indoor air quality monitoring with consumer grade sensors. I think for the most part, we're going to see a lot more open source devices like the BEVO beacon. So a lot of the studies that I was looking at related to the BEVO beacon from 2018, 19, 20 were very open source, not to the extent that the BEVO beacon was, but they had their code available to you, or they had the sensor specs, and so you can kind of understand their devices. And we're seeing more collaboration across disciplines. The BEVO beacon is one example. I was working with electrical engineers, environmental engineers, civil, mechanical engineers, computer scientists, even people from psychology, right, to build this device to make sure that it made sense. And we're going to see more of that, and that's kind of bridging that knowledge gap. We're also seeing standardized processes. So for calibration, the EPA has kind of released a tier list of how you can use your sensors if you hit certain criteria with your calibration. So if your calibration gets really good, returns really good agreement with the reference grade, then you can use it for research applications. If it doesn't, then you can use it for educational purposes. So that's a really nice way of kind of standardizing how we can use these sensors once we calibrate them. You have to calibrate them. In terms of software, these sensor companies are starting to release the software alongside the hardware, which is really cutting down on the time it takes to develop the brains and the inner workings of one of these sensors. And then I can't remember what organization, it's either the EPA or maybe some organization out of California, but they created libraries in Python and R specific to data analysis with consumer grade sensors. So specific to the data you get from these sensors. In terms of applications, we're seeing more individual and community level monitoring. So this is primarily more in the outdoor air quality community. A lot of governments are setting up, sensors all across their cities, which is great because people are starting to understand a little bit more about air quality and the effects it has on your health. These sensors are very much affordable. They can be tied into buildings, make them smarter, right? We can start to get things like energy savings. If you take a classroom that's not occupied for 4 hours in the morning, you don't need to ventilate that space. So if we can do some occupancy detection with things like CO2 and TVOCs and we don't notice anyone there, we don't necessarily need to cool it down as much as we might other spaces. Now, when that classroom starts to get occupied in the afternoon and we start to see more and more people in that space, then we can start to ventilate it more. We can detect that with CO2 and other sensors. And that allows us to get better thermal comfort and for spaces to feel more comfortable for people to work more efficiently when they're in there. And then lastly, this link between indoor air quality and human health, more specifically sleep quality, is we need more data. The relationships are complex, right? When you start dealing with something like sleep, which is affected by a variety of things, you have to kind of be careful that you're just not saying it's indoor air quality that's affecting it. And that's why we're kind of getting some contradictory results with kind of the study that we published, as well as some other studies in the related field. But ASHRAE, I believe, has kind of released a special issue or something related to that, where they're actually looking specifically at research targeting indoor air quality and sleep quality. So that's very promising, very exciting things coming down the pipeline. And then you have other organizations, like I went to a conference in May, the whole entire conference was about consumer grade low cost sensors, right? About how to use these sensors in a research context and what value they can give us. So really showing how consumer grade sensors can be used, in conjunction with these reference grade monitors to tackle some of these challenges that traditional monitors just can't do for us. So with that is the end of my presentation, but I have quite a few thank yous I would like to make. First, to my wonderful committee, my two co-advisors, Dr. Carrie Kinney and Dr. Zoltan Nagy. They definitely kind of epitomize those two groups that I kind of mentioned in that first research question. Dr. Carrie Kinney, very knowledgeable about the indoor environment, indoor air quality. Dr. Nagy, also knowledgeable about the indoor environment, but kind of comes from the robotics and sensors background. So definitely tying in those two ideas. Dr. Novoselic, he was my master's advisor. It's perfect that it shows him in the lab because that's kind of where he helped me the most, was setting up the calibrations and making sure my data quality was, at least up to his standards to a certain extent. And then Dr. Schneier, I don't believe he's here today, but he was kind of the black sheep of the group, but he's from psychology, kind of helped me understand the sleep quality components of things. So I wasn't, I think the big thing is he said not to say subjective sleep quality, was self-reported sleep quality. Just one thing I remember. In terms of other organizations, Whole Communities, Whole Health, they were the group of people that made all of this possible. So it's a UT Grand Challenge, really a multidisciplinary organization. They provided me the flexibility to kind of explore this idea between indoor air quality and sleep quality, which is kind of unique. I feel like most of the time as a graduate student, you kind of pick your advisor and they say, hey, here's the project, do it. This was more like, hey, here we have we have this opportunity, this experiment we're conducting. What kind of questions do you want to get answered? So really, really awesome that I was a part of that. We have people from nursing and I think from sports science, engineering disciplines, psychology, all over the map. So really, really neat to work with all these different researchers and really, really help to craft a better story because I was looking outside of just engineering. The Intelligent Environments Lab, this is the lab headed by Zoltan Nagy. So all these are my colleagues that spent, at least when labs were open, a lot of time in the lab with them. Definitely helped. Everyone here on this page was a huge contributor to the BEVO beacon primarily, helping me get the hardware and software all set up, helping me laser cut some of the devices as well. So absolutely, thank you to everyone here. My colleagues within the building, energy and environments, these are a mix of friends as well as people who helped me out in the lab. Definitely a nice support system. Great to see all these people in the lab and outside. So thank you to everyone there. And then lastly, of course, my support system outside of school. So my family, my fiance's family, and a few of my friends there on the right. Definitely great to have the support system and just have a way to kind of de-stress from the work, the graduate career. and to have some great conversation there. And the support they've had throughout these years has been absolutely awesome. And with that, that is it. So thank you all for your attention.